All right, I want to talk about IPv6. I'm seeing some interesting things in Juniper routers and also on my Windows computer when doing IPv6. So let's dig into this. First, I'd like to thank everybody who is interested in the channel. YouTube.com/@AaronTechTalk is my handle. And there's a lot of different videos here for various things related to networking. There's some videos where I mentored my son through his CCNA. There's videos about certification in Juniper or Cisco, and a lot of service provider related videos, which is where I spend most of my time working. Through the lifetime of my channel, which has been running for about a year and a half or so, we're almost up to 3,000 subscribers, so thank you very much. All right, IPv6, let's go. All right, to start with, in Windows, ipconfig is how you see your IP address. And on my Ethernet adapter, I have an IPv4 address. No IPv6 at all. And when we look at my Ethernet adapter, right click, go to properties, we find that IPv6 was unselected. Now, often these days, this is coming automatically pre-selected, so you probably would not have to do this in most modern operating systems. But I just wanted to demonstrate something, that when I select that and say OK, let's see what now happens. CLS clears the screen, up arrow, ipconfig. Now look at what we have. We have something known as a link local IPv6 address. If you go to Google and you type in IPv6 link local RFC request for comments, lists a few different RFCs here. I just wanted to learn real quick about which RFC might mention it. RFC 4291 to start with. If you're unfamiliar with RFCs, they'll quickly show you which RFCs are obsoleted by this one. So RFC 4291 obsoletes RFC 3513. Well, RFC 3513 obsoletes RFC 2373. Well, RFC 2373 obsoletes RFC 1884. So it looks like this is one of the earliest ones in December of 1995. Can you believe that? What's that? My gosh, almost 23, so 23 plus 28 years ago. IPv6 was getting standardized 28 years ago. Some of y'all are just learning about IPv6 in the year 2023. And I'm relearning IPv6 in the year 2023. Why? Because I forget stuff. And if you don't use it, you lose it, right? So for those who have not continued in their IPv6 deployment, you're probably going to have to refresh yourself with it. And there's a lot of interesting things, to put it mildly, a lot of different things with the IPv6 protocol, different than IPv4. So I came to this RFC and I did a Control F find on link local, link space local. It has one hit and it has this bit pattern, link local use address. So the first 8 bits are 1111, 1110. Copy that. If I get a calculator in Windows, there's your standard calculator, but if you go to programmer mode, click on binary, paste that in, and look what the hex equivalent is. FE is the equivalent of that binary pattern shown right there. Look at the next bits in the next octet, or the next hex character, however you want to look at it, in that IPv6 link local address is 10. So let's remember FE is the first bit pattern. We'll put that right there, FE. And let's look, the next one is 10. Now, you have to remember, this is just the leading bits of a nibble. Each hex character in an IPv6 address is a 4-bit nibble, okay? So that would be 10 with the trailing bits of being 0 as well. So there's two unspoken of zeros right there. So it's 1 0 0 0. So if we put that in here, 1 0 0 0 hex 8. So if we put that here, FE8. So this would form the first 3 hex characters of a very long IPv6 address. Let's fill in the rest of it. O colon and there are 8 total what are known as hextets. 3, 4, 5, 6, 7, 8. And I have too many colons there. So we see that according to the RFC, the bit pattern for link local addressing equates to the hex pattern FE80. So we enabled IPv6 on my Ethernet port, and if we look at the command prompt, we now see that we have an FE80 link local address that was enabled when we turned on IPv6 in this Windows computer. Now let's look inside of a Juniper device. And the devices we're working with are connected like this. Windows PC connected to a Juniper router. Connected to gigabit Ethernet 0/0/0. When we look at that port, here's what we see. It has an IPv4 address on it. To verify that, show interface. This shows the interface, and down here in the protocol INET field, INET standing for IP version 4 is what it actually means. Here is the IP address that I have on that interface. So we see the Juniper device is 172.31.10.204, and on Windows it is 172.31.10.243. So of this 172.31.10.0/24 subnet, Windows is .243, Juniper is .204. And looking in the Windows ARP cache, we can see ARP space -A. If we pipe to find, we can look for a specific string. 10.204 would be the MAC address of the Juniper device. And we can verify that by coming over here to the Juniper device and looking for 540680 on this actual gigabit interface as the hardware address, 540680. And vice versa, show ARP interface GE-0/0/0.0, no resolve. We find .243 is the Windows computer, and let's also look for that MAC address in Windows by looking at ipconfig, hit the arrow /all. We see that the MAC address for, if we roll the screen back up to where that interface was, we now see C2-8C97, and there we go, C2-8C97. Now I'm showing you all this to kind of set the stage for IPv6 and how it differs from what we know about IPv4. So we looked in the IPv4 ARP caches for address resolution protocol that resolves the IP address and its MAC address that corresponds with it. But this is not how IPv6 works. I'm going to start by configuring an IPv6 address on the gigabit Ethernet interface of the Juniper device. Family would be INET 6. That is what is known as IPv6. Let's put an address on there, and I'm just going to use a bogus address that I'm just dreaming up. 2000:2000:2000:111. :1 is the host portion, that lower number 1, and a /64 will be the mask. Let's commit and quit on that. I'm running Wireshark here in the back with some fairly extensive filters so that I can try to just pick up what occurs when this Juniper device configures itself with an IPv6 interface. Okay, there we go. We got a couple neighbor solicitation messages, and we will evaluate those. There we go. We see one come from that address, 2000, 2000, 2000, colon, 1111, colon, 1, is a ICMP version 6 neighbor advertisement. And when we look at that first one coming from our Unicast IPv6 address, it says that it is at 540680. Again, reminding ourselves of what the MAC address is of that gigabit Ethernet port of the Juniper device. 540680 is in fact what it is. If we look right below that, we see another neighbor advertisement, ICMP version 6, for the link local address of 54680. Now we need to remember that leading zeros are dropped in a hextet. So this would actually be 540680 in its fully expanded notation. So we see that the MAC address is embedded in the interface ID portion of this FE80 link local address. Now you might be thinking, well, this is 64 bits, and I know a MAC address is 48 bits. This is what is known as EUI64 conversion. So we know the MAC address is CC E194540680. Let's copy that. Let's put it in a notepad, and then let's look at the IPv6 link local address. If we show that interface again, and we go down to the bottom, we now see we not only have protocol INET for IP version 4, but we also have protocol INET 6 for IP version 6, and IP version 6 is capable of multiple addresses on an interface. We see the Unicast address that we configured, but IPv6 definitely has this new thing known as link local, the FE80 address that I've been talking about. It's completely unique to IP version 6. It is an address that is used on the link local subnet, on the local broadcast domain, and is not routable to other broadcast domains, or a router cannot route packets with the FE80 address in it. It's similar to the 224/24 subnet in IP version 4, but not exactly, because in IP version 6, every IPv6 host gets a link local address, and that's not true about link locals in IP version 4. So let's grab this last portion known as the IID, the interface ID in IP version 6, and let's see what extended unique identifier 64, EUI64, does to create this 64-bit address. So we've copied this. Actually, we only want the IID, the interface ID. Let's paste it into our notepad. And now we will try to make sense of this by putting it in the same format as the EUI64. Let's move this over and look at what we see. Let's put in leading zeros that were dropped in the compressed notation of IPv6. And now we see what was entered into the middle was FFFE. That is part of the EUI64 conversion process. One other thing is we see the difference of the second hex character, C, in the MAC address is now an E. What's going on here is the hex character, and we'll look at our calculator to help us with this conversion. Let's put in hex. C is binary 1100. So let's put that down here. 1100 equals C. What's happening in this second hex character, the EUI64 conversion process flips what is typically a 0, and it flips it and makes it a 1 of the second to the least significant bit. The most significant bits are on the, excuse me, I'm pointing the wrong way. Most significant bits are on the left side, and moving to the right are the least significant bits. So this is the most significant bit, this is the least significant bit, and the EUI64 process flips the second to the last least significant bit. So now let's put that bit pattern in our calculator, and we find that it's a hex E. So let's put that as an E, and now look what we see. During the EUI64 conversion process, two things happen. To take a 48-bit MAC address and turn it into a 64-bit IPv6 IID, interface ID. FFFE is inserted into the middle, and the second to the least significant bit of the second hex character is flipped. And there we have it, the finished product, which is what we find right here. I will say EUI64 is not the only way IIDs are automatically created. There's another random way that IPv6 IIDs are created, and it's for purposes of randomizing the MAC address so that it cannot be tracked. There's probably various other reasons behind it. Or you can manually create the IID, okay? If we continue looking at some of this traffic on the sniffer, we see the last few hex characters BF30 are in fact the Windows computer, BF30. So there's some IPv6 traffic that is being generated from that as well. Now remember, I told you that IPv6 Neighbor Discovery Protocol is how the neighbor solicitation works. This is the replacement in IPv6 for what we used to know as ARP and IPv4, a way of IPv6 resolving the IPv6 address to the MAC address. And where you find that is in the IPv6 neighbors table. So what we will do is I will copy over the Windows, or vice versa, I can copy over the Juniper address like this, the link local address, paste it into Windows, and ping it. And there we see we can ping the link local address of other hosts on our broadcast domain. So after pinging the link local address of the Juniper device from Windows, you can now see that in our neighbor table. In Windows, it's netsh, I think that might be netshell, interface IPv6 show neighbors. Let's see what that output is. A very long output. And if we go to the connection, we have multiple connections here. Let's go to the Ethernet port that we were concerned with, Ethernet port 2. We see 540680 is listed right here with its MAC address as reachable. And if we go back over to Juniper and show that IPv6 neighbor table, we see the opposite. Excuse me, ipconfig in Windows, we see BF30, we see BF30 in the neighbor table of the Juniper device with the actual MAC address. Now it says stale. If we do a ping again, let's see if it changes from stale. And not really exactly sure what causes it to go from stale to something else, but it stays stale even while pinging. Let's see if we can refresh it by clearing it. Clear IPv6 neighbor host. Says it's deleted. Let's ping it again. Let's go back over here. Now it says reachable. Now I want to show you something interesting with Windows Firewall. If we go over to the Juniper device, knowing good and well that we can ping from Windows to Juniper implies that we have bidirectional communications. We can ping and get a reply, okay? But when you go over to the Juniper device, let's see what we get when we try to ping the Windows computer. Look at this. We're not seeing any responses. The Windows firewall, or most firewalls, allow trusted to untrusted communications automatically. But from the untrusted side of a firewall, you have to open a port to allow traffic to come through. Interestingly, I have the Windows firewall enabled by default on my computer. Shown here, you can see that the Windows Defender firewall is enabled. If I just go here, turn Windows Defender off, just click off for a moment on both of these, and I say OK, look at that. The pings immediately start coming back from the Juniper trying to ping the link local of the Windows device. And as soon as I re-enable that, I see that I can no longer get pings to come from the Juniper to Windows. But we do see that the Windows to Juniper continue to flow. This is just the nature of firewalls. But I do want you to realize that you're not stopping the neighbor discovery process with firewalls, and you shouldn't. This happens automatically. That's why we saw the neighbor cache was instantiated even when the firewall was enabled, okay? And if we look at those pings from Windows to the Juniper, we see those pings are flowing in the sniffer. That is ICMP version 6, and we see that it is echo request, echo reply. Okay, that's all I got for this video. We'll see you later.